All right, so my name is Juan, or Camilo, Juan Camilo, and I'm going to be talking about the tips, the tricks and hacks and other principal design decisions that we use to train underwater robot to how to swim. So the goal of our lab is to develop adaptive systems, adaptive autonomous systems for data collection. So the idea is that we would like to provide tools for scientists to collect data in situations where it would be really hard to control a robot with a joypad or with some other user interface. So in this talk, I will talk about mainly three things. I will describe the AQUA robot, then I'll describe our simulation environment, which we develop on top of Gazebo. And finally, I'll talk a bit about our experience with applying reinforcement learning algorithms to the AQUA robot. So the AQUA robot is an amphibious six-legged robot capable of autonomous operation. Its propulsion system is based on 6 flippers, so it just moves its flippers and it gets propulsion in the opposite direction. It's based on the Rex walking platform. And, this underwater version was developed at McGill University. We used to be one of the only 2 labs in the world using this robot, but in the past few years, there's more people getting them. So I encourage you to go visit their websites to see what they're up to, how they're using the AQUA robot. The AQUA robot hardware is very similar to what you would find inside a drone. It's essentially a low-level computer that interacts with the motors, internal sensors, power management. A high-level computer that we use for vision tasks and where we actually put all our ROS stack. And all of it is connected through an Ethernet switch, which we can also connect to some external payload. So, for example, we connect it to acoustic devices for localization underwater. We also have a fiber optic to Ethernet link, which allows us to connect an external PC for monitoring or deploying other algorithms. So I'll talk a little bit about the software that we use for control. So we have the control stack that it's running a 1 kilohertz real-time loop. This is what interacts directly with the sensors, the low-level sensors and the motors. Then we have the vision stack where we drop all our ROS software. So we have some ROS interface for the hardware, some ROS packages for navigation, and some packages for user interface. And then another big part of what I'm going to be presenting today is our controller learning architecture, which is also built on top of ROS. So the hardware interface is essentially one package that defines all the messages that we use internally for passing data around about the robot state, and one package that it acts as the layer between the low-level control and ROS. For navigation, we have the AQUA Autopilot package, which implements trajectory tracking via waypoints. So we control the robot's pose by setting waypoints on its 6DOF world. And we use some extra packages to transform the sensor streams into the ROS and TF conventions. For the user interface, we used to use, we modified the Joy package to interact directly with our autopilot with this idea of setting waypoints to change the robot's pose. So all this ROS-based software has enabled us to, for example, program the robot to perform certain maneuvers to point its sensors in any direction that we want. We can do this using just the autopilot package, but we have to spend a lot of time tuning all the controller parameters to get all these maneuvers. So tuning these controllers, it probably took a couple, I would say, days. So that's why we're looking into learning these controllers instead. Another application that we're going to be presenting at IROS is convoying with the robots. So the idea is that we can have one robot that deals with global localization using an acoustic sensor, And we let a robot behind it carry another sensor payload and not worry about a lot about localization or control. We just put in there a really simple tracking controller, a reactive controller to follow the leader. So now we can go into the description of our simulated environment that enable a lot of the development and debugging of this software. So going back to that software overview, we just swap out our control stack and our vision stack, and we just put Gazebo in. So we develop a couple plugins and use a couple other plugins that existed already to emulate the AQUA robot hardware and simulate the underwater robot dynamics. That thing is running at 1 kilohertz, just as the real hardware. And then on a developing machine, we just run the rest of our software stack. So emulating the AQUA hardware consists of a plugin that just implements the same interface as our AQUA hardware package. We use the IMU sensor plugin from Gazebo ROSC that works fine for our simulations. Then we add 2 plugins to simulate the additional underwater forces and the propulsion model, since we're not simulating the fluid around the robot. So for simulating the hydrodynamics, what we do, it's very similar to what the aerodynamic drag from the presentation on self-driving cars. We just add everything as external forces. We let ODE do its own integration loop as usual, and then we model drag, added mass, buoyancy as forces that we need to add to the simulation. So we have 2 ways of simulating the hydrodynamics. One is using a box model, so we just go through all the geometry of the robot, and we just put boxes around every link and compute the drag, assuming that every link is boxed. We also implemented one idea that was published in SIGGRAPH a couple years ago, which is based on the mesh of the geometry. So I'll explain a little bit more about the mesh. So for the mesh method. So for buoyancy, what we do is we traverse the whole geometry tree of the robot. We compute the volume for each link, and we apply the buoyancy force that is proportional to the volume of displaced liquid. And that force is going in the opposite direction of the gravitational force. Ideally, you should be not adding 2 different forces like gravity and buoyancy and then integrating that, but rather you should consider, like ODE internally integrates gravity separately. So we should be putting buoyancy there. But since that's not directly available through the Gazebo API, we just did it with an external force. For added mass and drag, what we do is we take the collision geometry of each link. So the collision geometry, in our case, it's a really simplified version of the visual geometry. So it's like 1% of the vertices. And then we can pre-compute 2 matrices that essentially these are linear relationships between velocities and forces. So one is the drag tensor. It's just drag times velocity. It produces some force in the opposite direction of the displacement. So it models like the hydrodynamic drag. And we have added mass, which means when the robot is moving underwater, it's also displacing some liquid. So when it's stopping, it has to also stop the liquid. So it acts, the water around it adds mass to the system. So this is modeled as a matrix multiplication that produces momentum. So essentially, added mass here, it's mass times velocity, it gives momentum. To get it as an external force, we just integrate it over time, and we get an expression for the force that we need to apply to each link. For the flippers, we could just say, use the hydrodynamics that we're already simulating and see if that produces thrust. Well, for periodic motion, all these forces will cancel out and the robot will not move. Propulsion, the way it happens with fish and with flexible flippers in our case, is that when the flipper is moving, it's shedding vortices. And when the flipper hits one of the vortices that it has shed before, that produces some force, some propulsive force in the forward direction. So since we are not simulating the fluid, and since simulating the fluid will take a long time, we just use a very simple empirical model that essentially produces a propulsive force that is proportional to the amplitude of the periodic motion and inversely proportional to the frequency. So we use the parameters that were found on the reference by Plamondon and Nau. And it seems to work, at least it gives plausible results. So here's an example of a simulation on where we were just dropping the robot underwater and seeing how it behaved. And so our idea is that one of these experiments, like learning how to stabilize, if we wanted to run that experiment on the real robot, we would have to pick up the robot, throw it into the pool, go to the bottom of the pool, pick up the robot again, throw it again. So using simulation enables us to avoid that kind of work. So is this simulation accurate? Probably not, because we're not simulating vortex shedding or the whole fluid that's moving around the robot system. But it gives a reasonable or plausible behavior of prediction of how the system would behave. We found, surprisingly, that some of the controller parameters for the autopilot on the real robot actually worked on the simulation. So that must mean that maybe the simulation is capturing some of the effects that we see in the real robot. And well, we are also looking at improving these models with real experiment data. So the idea is to use the simulation as some sort of informative mean prior, and then add corrections from the stochastic world. Finally, I'm going to talk a little bit about our architecture for motor control learning. So I guess the whole idea is that we're going to use reinforcement learning where an agent, a software agent, it's presented with two streams, uninterpreted streams of sensor data and control data. And it's going to learn how to act or how to perform a task via trial and error. And we usually specify a task with some objective or reward function. And the problem here is then the agent has to find a controller that realizes the task or maximizing reward. So now the whole idea of reinforcement learning algorithms is that you replace your design effort where you're trying to figure out what are the situations that the robot is going to encounter in the future with letting the robot do experiments by itself. Well, the problem with trial and error is that, again, going back to that robot diving example, is that if your robot does not know how to recover, then you need a person to go pick it up. So an alternative to robot experiments, and this is like the vision of where we want to get to, is that we first learn the basics on a low-cost simulator, like for example, there on some airplane simulator where people are pushing you, and then once your instructor thinks you're ready, then you can try your skills on the real deal and try to minimize failures by minimizing interactions with the real system. So one thing that we found when trying to implement reinforcement learning algorithms with a ROS-enabled robot is that there's no straightforward way. Like you have all these generic reinforcement learning libraries and some very specific robot software. It was not clear for us how to glue everything together. So here's like our attempted solution at that problem. So for my own research, I developed this library of a suite of reinforcement learning algorithms that I think are applicable to robotics because of their data efficiency. So, and I implemented a bunch of different controllers for different tasks. I'm going to be releasing this code pretty soon, because I like people to reproduce the experiments that I've been doing on my research. But if it's not there yet, but if you want it, just contact me and I can send you the code. The other building block of our learning architecture are this task marshalling module and the glue that connects the reinforcement learning library with ROS. So what we usually do in our experiments is we don't learn just one learning experiment because deployments are costly. We want to learn multiple tasks at the same time. So we let the system try task 1, then task 2 sequentially, and offload all the learning to happen in some remote server. Since all this learning can happen at different times, we need some way of triggering when the robot is ready to gather more experience. So that's what AQUA Marshal does. And then the Kusanagi ROS package, what it does is converting the interpreted topics from the ROS world into the uninterpreted sensor streams that RL algorithm expects. And the way we do this is we just wrote a simple node that converts topics to to RL streams. Essentially, we have a node that reads a YAML file that tells it, subscribe to all these topics and put them out in some desired format, usually just a single vector. And we have a similar thing like for any control command that comes from the controller, we can tell it, publish it to all these different control topics. Finally, this is how we connected everything together. So the whole pipeline is, we have a robot that it's executing some controllers. Then using our learning interface, we send the experience data out to the offsite learning server. And then over time, we're getting new parameters to try out. And we use a joypad to be able to drive the robot to some initial state and then say, now you can try it again. So here's an example of a learning run for a single task. So here the robot is trying to learn how to do a barrel roll while swimming. So it's getting new data, it's building a new model, and using this new model to optimize a controller. And over time, you see it's pretty quickly, it can get to learn the task here, swimming, doing that corkscrew maneuver. The main problem with this is that learning still takes a long time. So even if we're able to maximize the amount of, minimize the idle time of the robot in the pool, still these experiments could take up to 4 or 5 hours, and that can be quite tiring for the people, for the graduate students running the experiments. So what's next on our world? We have the tools for training robots in simulation, and now we want to run the experiments that or close the loop between the two, like learning simulation, gather new experience in the real world, update the simulator, and continue improving over time. One of the things that we found is the machine learning community has done a lot of progress because they have tools for easily implementing learning algorithms and running experiments with them. And the question is is what they're doing robotics? Well, some people would say no, because it's missing these are idealized worlds. So I guess one thing that I would like to see in the community is more of this ease of running experiments on ROS-enabled robots, just as you would run some experiment on one of these RoboSchool robots. So in summary, I gave an overview of the packages that we use for motor control on the AQUA robot. I told you a little bit about our simulation environment. And I also gave you a brief description of our reinforcement learning pipeline and how we plan to use it for simulator to robot transfer. We'll be releasing some of these packages in our GitHub. So I think in the next couple of weeks, you should be seeing some of them. Again, if you want to get them now, just contact me and we'll see what we can do. So I would like to thank you, the audience, and also all my colleagues at the Mobile Robotics Laboratory who have contributed to this project. So thank you.
Thank you, Juan Camilo. Gajar Mohan, can you come up, start getting set up? I think we have time for one quick question, if anyone has questions.
So you showed your learning with this AQUA robot, but would the interface between learning and ROS and also your learning code work on other platforms already right now?
Yes, because our code, it's robot agnostic. Like we're all converting all these topics into just uninterpreted sensor streams. So you could potentially use it with any other robot.
OK, one more thank you for Juan.